Dear friends, welcome to today's seminar. I'm pleased to introduce you Dr. Erdinç Tatar. He is a graduate of this department, and then we had worked together for a while, and he completed his master's degree in this department, working with the MEMS Center also. And then he went to Carnegie Mellon University and worked with some of my friends over there. He got his PhD, and then he worked in analog devices for 2 years. And he recently returned to Bilkent University, and we hope to work with him also in the future. So I'm looking forward to this presentation.
Thank you. So it's my pleasure to be here. So thanks for inviting me. So today I will mostly talk about my PhD thesis, and afterwards, at the end, so I will tell you what my plans are. So my main study was based on finding solutions to the sensor drift problem, or more specifically gyroscope drift problem. If you look at many sensors, the main problem, or one major problem for most of the sensors, is drift. So how we can understand drift is, so this is my sensor output, in this case a gyroscope output. So I'm not rotating the gyroscope, it's sitting on the table. I'm not applying any stimulus. And if you don't apply any stimulus to a sensor, what you expect is its output shouldn't move. But here, if you look at this red curve, so it's going somewhere, although I'm not applying any stimulus. So this is a drift problem. And this thing is happening very slowly. So if you look, this is like 12 hours. So it drifts very slowly in 12 hours. And our goal was, so this drift problem has been there forever. People first attempted to fix temperature. So they thought the source of this drift is temperature. And they fixed the temperature, and it was still drifting, and I'm kind of showing it here. So here I have a plot of temperature versus breakiness, which I will explain later, but the temperature is very stable, like 40 millikelvin stable, and it's still drifting. So the goal here was, if we focus on stress compensation, so instead of temperature, or in addition to temperature, can we solve this problem? So I'm telling you the final result here, so we solved the problem, and I'll explain how. So this is the gyroscope that I studied in my thesis. So this is a three-fold symmetric gyroscope. It has an x-axis, y-axis, and it's also symmetric on diagonally. So it's three-fold symmetric is what it's called. And the anchors are marked with black here. So the anchors are very important in maps in general, because anchors are the only way that your device can interact with its environment. And what happens is, so your gyroscope is made of silicon, and you mount this in a package which is not silicon, and there will be a temperature coefficient of expansion mismatch, so that's called TCE, between your device and surroundings. So once temperature changes, then your anchors and your package wants to move differently, and that causes some stress on the device. So this is a temperature-induced stress. There are other stress sources which are not temperature-induced. So one big example is aging, for example. So these devices are mounted onto substrates with certain glues. You can think of it as a glue, and it's called die attached. And that material is a polymer in general, and it ages. It absorbs moisture. With temperature, its characteristics change, and when the temperature comes back to its original place, the material is not the same. And that causes non-temperature induced stress. And when you just look at temperature, so you can't see it. So as I said, so the goal is doing stress compensation, and for that reason, so I put the gyro in the middle, and I have stress sensors surrounding the gyro. And this stress compensation has to be on chip, because the stress is very position dependent. If you put it somewhere else, it is very likely that your device and your stress sensor will see a different stress. So, and the stress sensors are on the side. The other thing I studied was non-linearity. So I will explain this to you. So this device operates by displacing X or Y, and the more it displaces, the better signal-to-noise ratio you get. But as you increase the displacement, you run into certain issues. One of them is non-linearity.
computer?
It's my computer.
Okay, so you will explain us what is a gyroscope.
Yes, next I will explain you what is a gyroscope. So the gyroscope works on Coriolis Force. So what is a Coriolis Force? Some of you might have seen it, some science museums.
What is a gyroscope?
Gyroscope measures rotation.
Okay. So.
Oh, I'm sorry. That's step number 1. Gyroscope measures rotation.
Okay.
I assumed you know it, and I should. So it operates based on a Coriolis force. So some of you might have seen this if you go to a science museum, some of them has it. So if you have a pendulum like this, you have a ball, you attach a ball to it and you attach to the ceiling. You pull and release the ball, so the ball starts going back and forth. So initially it's doing this, but if you wait long enough, what you will see is it will change its trajectory. So it will spin around this circle. And if you wait long enough, and assuming there are no energy losses or somehow you compensate them, this thing will keep rotating. And the reason for that is it's following the Earth's rotation, since the Earth is rotating, and this is trying to follow it, and that is modeled by this Coriolis force. So while this ball is going back and forth, there is a force that's acting it orthogonally so that it follows this circle. And that this force is Coriolis force. It depends on the applied rotation rate and the velocity of your signal, of your ball. And so if we were to do this experiment in Ankara, so if you think of the Earth, so the Earth is a sphere. If you hang this ball on the poles, I will see the exact rotation, so it will be 15 degrees per hour. But Ankara is not on the poles, or if you do it on the equator, then it will see zero force, because then they will be orthogonal to each other. But if we do it here, the latitude of Ankara is like 40 degrees. If we do this, what we will see is sine of the latitude times 15. We will see close to 10 degrees per hour. Or in order to see this ball rotate the whole circle, you have to wait like 37 hours. And in this, while you are following this, you have to somehow compensate.
Where does that 15 coming from?
The Earth rotates at 360 degrees in 24 hours, and it's 15 degrees per hour. Actually, it's not 15. When I looked at the exact number, it's the Earth completes its rotation 23 hours something. Slightly less than 24. And how do we do this in the man's gyro world? So in order to have Coriolis force, you need to have some sort of velocity. That's why we pick one axis, we call it drive, and we drive the mass into resonance. While the mass is going back and forth, if it's rotated about the z-axis, because your velocity and your rotation have to be orthogonal to each other, then there will be another force in y, and this will force this mass into vibrate in the y-axis as well. And when you pick up the signal in the y-axis, that's your rotation. So this is the fundamental principle, but making it stable and making it not drifting is the main goal in these days. And
So
how do we measure?
This rotation is not due to the Earth rotation. This rotation is,
Yes.
if you send something,
If
it rotates,
when the
you
frame
can
of the
sense it.
gyro rotates. I mean, you can measure the Earth's rotation as well. This will measure it, but by the time you turn it on, it's measuring and you can't see the difference. So you have to do some sort of, that's called carousel, some sort of trick. And how do we measure the performance of a gyroscope? So this Allen deviation test is very famous, not in the gyro world, everywhere. So what you do is you collect your sensor data, and then you plot the variation of your sensor data with respect to different averaging times, which is tau. So if you have pure white noise, so pure white noise you can suppress by averaging more and more. So it goes down with the square root of averaging time. But after a certain time, your averaging doesn't work because other noise sources start to kick in. And then it reaches to a 1 over f noise floor. So this is like the 1 over f or 1 over f equivalent of gyros. And if you wait longer, then it will keep increasing because then the gyro output is like what I showed you in the first slide. It's following a line or some sort of trajectory. Then it starts to increase. So why do we plot this? Because we want to get the most out of the gyro and the best resolution. And we can do it by averaging, but up to a certain extent. So after a while, if you increase your averaging time too much, then you will start to see increase in your noise again. So what are the application areas? So MEMS in general tries to minimize and make things smaller and make them cheaper. So the biggest example is accelerometers. So accelerometers are very widely used. So its application area is a lot more than the gyro. You can find an accelerometer everywhere. And the reason every car has an airbag today is because of the MEMS accelerometers. The MEMS accelerometers made the airbags cheaper, such that it can be implemented in every car. So gyroscopes are following a similar path, but not the usage is not as much as the excess. So some of the application areas, so most of, I think all of you has a phone, a smartphone, and the cameras, I think most of them has this optical image stabilization as well. So optical image stabilization is when you are holding the phone and if your hand is shaking back and forth, left and right, then wherever the camera is looking is shifting. And with a gyro, they understand how much you are rotating your hand and they manipulate where the camera is looking. So that's optical image stabilization. So it's in the cars, so electronic stability control, ESC, if you heard this. So in a car, there is a gyro, and they continuously measure your steering angle. So you steer towards left, and they measure the car's rotation. So if there is a mismatch in between your steering wheel and what the gyro is measuring, then that means your car is slipping or doing something that's not desired. In that case, in order to match it, so the car applies different brakes to different wheels and corrects the car. So in platform stabilization, these are widely used. For example, for a drone to stay like this, it has to measure that it's flat, and whenever it turns, it flips left or right, then it has to correct itself. And that's done with a gyro, and it also has a camera, and K-camera also has one more gyro. I believe this has 2 gyros in it. Inertial measurement units, so it's when you have 3 gyros and 3 accels, then you can measure X, Y, Z rotation and linear acceleration, and you make an IMU, and ideally, when you are navigating, you use GPS. GPS can be jammed, but this, in order to misguide the gyro or accel, you have to change the gravity. These things are very robust, but the problem is not as accurate. They drift with time, and in the navigation you take the integral of gyro and accelerometer and the errors build up. So one application area for IMUs is the big one that's coming, is autonomous cars. So when the car is driving by itself, so it uses GPS, it uses cameras, it uses LiDAR, it uses radar, but at the end, all of them may have failed. For example, you can use the GPS signal. The weather is very rainy, the camera cannot see, or very dark. And in that case, these IMUs are used as the final defense line. So if you lose everything, then the job of the IMU is bring the car to a stop within a certain, like 100 meters or so, safely. So most of what we do, most of the MEMS is two-dimensional. So whatever you see because it's coming from the IC manufacturing principles, so everything is 2D. And most of the gyros that are done are also 2D. So whatever you see in the screen, just extrude it towards yourself, and that's your device. But there is some effort to do 3D gyros too. So and whenever you read a gyro paper, they somehow refer to this gyro. It's called HRG, Hemispherical Resonating Gyroscope. Northrop Grumman, a big defense company in the US, manufactured this, I think 10 or 20 years ago. So it has a 3 centimeter diameter, so you see it right next to a US line, so it's 3 centimeters. But its performance is incredible, so no one can catch these performance numbers. So if you're in the gyro world, so bias instability of 1 is good in general. This has 10 to the minus 5 right next to it, so it is extremely accurate and extremely low noise. And one example, so it has a quality factor of 26 million by making reasonable assumptions. So if you just ping this device, it will ring for 12 minutes. So it is so low loss, and they made it so perfect. But the problem is, if you want to buy this, I don't think they will sell it to you, first of all, because it's so high performance. They put it on the satellites or whenever they send something to space, or like big telescopes when they watch the space. The problem is that it's $100,000 per axis. So it's extremely expensive. And So there is an effort. DARPA has been supporting this 3D gyros, but only 2 of them survived, and they have been supporting it for up to 10 years. Only 2 of them survived. So these are lower cost versions of this. So this is a 1 centimeter. So this is manufactured by University of Michigan. It's called a Bilkent resonator. But the problem is when you manufacture this to sense it electrically or to drive it electrically, you have to put electrodes around this. And this is a 3D structure. So that's a major problem. So these guys are still working. They have some results too, but it's far away from being commercialized. And you see Irvine also doing this, they call it wine glass resonator. The manufacturing principles, I'm not going to those details, different, but there is such an effort, which is which has not reached its final result yet. Gyroscope equation, so how do we model this? Whether it's a wine glass or a 2D structure, it's modeled the same. So you basically have 2 resonators. So this is a single axis gyro, by the way. So there are 3 X, Y, Z rotations. So this is just 1 axis. So you have a drive mode, you resonate it in X, and whenever there's a rotation about the Z axis, then that couples a force to the Y channel, and you measure that force. So this is like second order spring mass damper or Rlc system. Same here. The drive is driven, the sense axis, which is Y here, it is driven by the force that originates from the drive. And you can operate in different conditions. You can either match the resonance frequencies of X or Y, or you can make them very separate. So this is when you make them very separate, when the delta omega is the difference in between X and Y frequency. Then your sensitivity is less, but your gyro is more stable. You can match the resonance frequency of X and Y. So there is not a commercial product that is doing it, I believe, and it has a lot of drift sources in it. So we have to dive into details, which I will not right now. But most of the gyros operate in a what we call frequency split mode. The frequency of X and Y are different. And stress and temperature, that's the main focus area of us. Stress and temperature modify the resonance frequencies, modify the gaps, modify the quality factors, and that results in an unwanted shift in the output. And stress has been studied. As I said, the die attach, so this is your sensor and this is your package, for example. So this is the same for all ICs. It's manufactured on silicon and it's somehow mounted somewhere. And you use an adhesive, and the properties of that adhesive, not as important in the IC industry, but it's very important in the MEMS industry. Because this adhesive is basically determining how much external stress comes into your die. And you want to make it stable, very soft. For example, if you don't want any stress come to your device, you want to make your adhesive very soft. But if you make it very soft, then the problem is it becomes humidity sensitive, and it absorbs moisture and it causes different stress on your device, which cannot be understood very well. So people try to optimize the adhesives. You have to make it soft. Or they did something like this, where you mount your device on the bottom, so that it's very compliant. Whenever external stress comes in, this relieves the stress. But as you can imagine, this is not very easy to manufacture. And people attempted to solve it through design too. So this is called disc resonating gyroscope. The Boeing owns this gyro. And what they do is they have a central anchor, and then the other anchors are around the device. So this has a more centralized anchor scheme, which helps to suppress the stress effects. Or you can do other tricks, such as you take your gyro, you don't mount it from everywhere, you just mount it from the center. Also that minimizes. But whatever you do this or that, you may suppress the long-term drift. Long-term drift is the problem that we are trying to solve, still exists. And even the state-of-the-art gyros have some sort of drift. By drift, I mean if you look at the L invariance, and then in the long term, if you see an increase on the L invariance, if it's like U-shaped, then you have drift. Let me talk about non-linearity for a while. So we like high drive displacement, or we want to displace as much as we can, because that increases our signal to noise ratio. But for MEMS, if you increase your displacement, normally this is up to this mx dx kx, it's your linear equation. But if you displace too much, then k3 times x cubed is introduced. You can think of this: if you have a beam and if you pull it, initially it's linear in between your force and displacement, but once you pass certain point, it becomes harder and harder to bend. And that's called the hardening nonlinearity, and it's related with cubic stiffness, and it's K3 times X cubed is how you put into equations. So this is on the mechanical domain. So what I was doing, or most of the gyros are capacitor, and these capacitors are not ideal. So they also have some sort of capacitance in between this tip and the anchor. And what is capacitance? Epsilon A over gap. And that gap change is a nonlinear change, and that causes another nonlinearity. So these are different. One of them is hardening. That makes things stiffer. This one is softening. This makes life softer. So they work in different directions. And what is the problem? So you probably have seen what is the response of an Rlc circuit. So when you do a frequency sweep versus amplitude, what you see is this blue curve, which is nice. Or when you do the phase, so this is amplitude, this is phase, you will do a continuous phase, the blue curve again. But if you increase the displacement, what happens is these curves start to become like bend towards left or right. So if it's bending towards right, that's hardening, so it's getting harder. When it's bending towards left, it's softening. So the problem here is, if I go from one amplitude to the other, my frequency is not the same. And that's called the amplitude frequency effect. So as you increase your amplitude, your frequency changes. And in the real life, so you don't see this if you do a frequency sweep, because look at this, at a certain frequency you have two amplitudes. This is not possible in the real life. What happens is, in the real life, depending on if you are going left to right or right to left, this thing comes and then jumps. So you'll see like shark fin type things. And we want to increase the displacement, but then we run into this nonlinearity issue. And what we proposed was, we proposed a type of finger, which is DC voltage controlled, and it can introduce certain type of nonlinearity, and we can cancel this and make it linear. I'll show the results. So this is the fabricated version of the gyroscope. So this is stress sensors on the sides. So in terms of size, I think this is like 2.5 millimeter from side to side. This center is 1 millimeter square, and you see the different fingers. So in I don't want to say conventional, but in most of MEMS, what you see is you see straight fingers like this. So what we did was we shaped the fingers. These are not this like fork shape, and this is like a tube shape. And I will explain what these things are doing. So this is something new. So this gyroscope wasn't invented by me actually. Similar gyroscopes have been done here like around 2000s and done in Carnegie Mellon in the past as well, and UC is still working on that type of design. So what is new in this gyro was not the gyro itself, but stress sensing and these frequency and nonlinearity tuning fingers. And this is a more cartoon view. How does a gyro work? So this is during real operation, so you can think this as drive, so it resonates back and forth. And whenever there is a rotation, the other axis starts to vibrate too, and you pick up the current output from that mode and convert into voltage, and that's your rotational rate. And our fingers are all, they exist left, right, up, down in a symmetric way, and the shaped fingers are controlled by DC voltages, and these regular combs, regular capacitors are used to control the gyro or make the gyro work as it's supposed to. So stress, as I mentioned, so this is our system again, and I wrote down the equations in a matrix format here. So when we apply stress, by stress I mean your anchors move. So when your anchors move, that will induce some sort of changes on your device. So it makes your alignment not perfect, your gaps changes, the symmetry is broken, and your spring constants, so when it's written this way, this kxy and kyx is called quadrature error. So this is one of the main headaches of the gyros. Quadrature error is in general like 3 orders of magnitude larger than the signal you want to measure. So it induces this quadrature error, and it changes your force. And the most important thing is, if it modifies your gaps, then that change cannot be distinguished from Coriolis signal. The gyroscopes, one main principle is they work on phase-sensitive demodulation. In a gyro, everything is phase, so you have to pay attention to phase extremely. And because some signals are 90 degrees out of phase from your main signal, So that's why when it's out of phase, if you do a phase-sensitive demodulation, if you multiply the signals properly, then you can get rid of them. But some of them, like when you apply stress, it comes at the same phase as your main signal. And that signal, then there is no way you can get rid of that signal. And stress calibration comes into play at that point. So I will show you one example here. So this is a cross-section of my device. So these things are springs. This is folded spring. So that it has inner beams and outer beams. The inner beams are these two on the center, and the outer ones are on the outer surface. And when you want to compute the spring constant of this beam, then it is the series combination of inner beams and outer beams. So this is very similar to having two resistors in parallel. But when we apply stress, if you compress this, for example, the dashed lines are its original form, and then when it becomes blue, then the inner beams will see compressive stress, so you are compressing them. But the outer beams, since it's pushing outer beams, they will see tensile. And that changes their spring constant in different ways. And what happens is, like you have two parallel resistors, and the equivalent resistance goes down if just one of them goes down. And this is the same thing here. So whenever you apply stress to this type of structure, whether you compress it or expand it, the resonance frequency always goes down. And we were doing it with temperature, so there's also temperature, and the temperature change is a line, and if you superimpose both of them, then you end up something like this. So this curve is important, so in my measurements, I will show you why this is important. We also developed a simulation scheme to simulate this, because using finite element analysis, you can simulate the frequencies and stuff, but if you want to include the electronics, it becomes very confusing and very difficult. So for that reason, we use cadence, and we first run a finite element analysis. We get our anchor displacements, and then we input it into cadence, and cadence has the behavioral model of our gyro. And using that behavioral model, then I can use the entire cadence. I can do AC analysis, transient, DC analysis, whatever I want. And this is called MODIS, Model Design of Actuators and Sensors, is what it stands for. And we use this to simulate the gyro, and this is one result. So this may be very confusing to you. So this is an AC analysis. I sweep the frequency and I look at the phase and displacement. So here, what we showed at the end was, even though you operate ideal conditions, you end up with, whenever you apply stress, you end up with an offset, which is 8 degrees per hour here. And you have to pay attention to other stuff as well. So this is the transimpedance amplifier that's used to read the output of the gyro. But there is something called feed-through capacitance. So there is a capacitance in between your AC drive to this pickoff, and that also affects things. Gyroscope control. So the reason gyroscopes are not as common usage as accelerometers is they are complex. So this is like the control structure of a gyro. In an Excel, you have two blocks. You just read the output in general. But here, so it has a dry mode and sense mode. In order to, so we have to lock into the resonance frequency. For that, we have a PLL on the dry mode. So once you lock into the frequency locking is not enough. Then you also need to fix the amplitude of the oscillation so that your Coriolis force becomes stable. So that's number 2. That's amplitude control. And when you come to the sense mode, the phase-sensitive demodulation I mentioned, there is a quadrature and rate. And in general, you have to control this quadrature because this is 3 to 4 orders magnitude greater than your signal. So in order to suppress this, you need one more loop. That's number 3. And number 4 is you don't need to close the loop on the rate. You can operate open loop, but it's better if you close the loop. That's number 4. So what I'm not showing here is if you want to match the resonance frequencies of X and Y, that's another loop. So that's number 5. So you need 5 control loops, or minimum 3, to operate the gyro. And how did we do this? So this is my gyro. This is in a package, and I have electronics on the PCB. And there is a lock-in amplifier. It's Zurich Instruments is the name. Everybody uses it. It's very common in the inertial world. And it has all the phase lock loops, controllers, amplitude control. So I convert the output of my gyro to voltage, input it into the Lock-in amplifier, and control signals come back from the Lock-in amplifier, and you can make a gyro like that. And I also have stress sensors, so they are strain gauges, resistive bridges, and I have stable voltages on the board that I apply to the stress sensors. And you have to manufacture this somehow. So I was using a relatively simple process. This is called SOI MEMS processing. So you get an SOI wafer, silicon on insulator. So you first define your paths such that you can wire bond to it. And then in the second mask, so it's a two-mask process, you define your structural layer by using deep reactive ion etching. And finally, so this doesn't require any processing, I coat chrome gold on the backside of the wafer so that I can solder it to my package. So the problem was in this deep array step, the deep array MEMS has the SOI notch option, but ours didn't, and it turned out to be that's a useful option. If you don't have it, things don't work. So then what happens is deep reactive ion etching cycles in between etch and passivation, and during etch there is an ion bombardment, and in that ion bombardment when you reach this oxide, the ions are captured by the oxide, and the oxide charges, and when you send more ions, they scatter, and if you get the backside of your device, it removes your backside as well. So if you have the SOI notch option, I think they pulse that ion bombardment and it doesn't charge as much. And the solution was, what we did was, so these are process specific parameters, we basically slowed down the edge and make it more passivation, less edge, and we ended up relatively better results. So if you use it like this, then what happens is one silicon piece bridges from this to the other side, and you end up seeing different resistance in between. So fabrication, second one is packaging. MEMS, whatever it is, whether it requires vacuum or not, it has to be packaged because it's very fragile. So in the case of gyroscopes, you need vacuum packaging because this device is so small that it's affected by air. And if you want to drive it into resonance, if it's in vacuum, you can do everything better and with smaller voltages. So you can do the vacuum packaging two ways. You either do it at the process at the wafer level, but if you don't have that option, you can do discrete level vacuum packaging is what this is called. So I have a ceramic package and my device is in the middle. So I was doing this in a unique way. So what I did was, so I have a like aluminum tool here. The MEMS device sits in this aluminum tool. You apply vacuum and then it holds it in place because you put it outside and then bring it here. So I found something called nanofoil. So this nanofoil it's a trade secret for the company who sells this. So it has plated tin on both sides, but whenever you apply a voltage pulse or a laser pulse, an exothermic reaction starts in this nanofoil, and it melts the tin on both sides and it solders your device to the package. So the advantage here, whenever you solder or use a glue, generally you have to cure them, like greater than 100 degrees. For soldering, you have to go to 200 or even 300 degrees Celsius, but this happens at room temperature. And when you go to that high temperature, so whenever the glue melts, your device is in zero stress state, but it will freeze when it passes its melting point, and then when you come back to the room temperature, then it will induce stress. So this thing, since it happens at room temperature, there is no stress, was the point. So we are not over, so we mounted in the device into the package. The next is I have to seal a lid to this package in vacuum. So there are companies who sells this type of systems. SSD furnaces is one famous one. So if you go to them and then if you ask, they will tell you it's $500,000 the equipment. So we had to do it by ourselves too. So I have a vacuum chamber. It has pumps and I have my package here and I can move. So this package sits into this aluminum mold upside down, and I have a heater here. So first I put my lid, and then I heat the lid to a very high temperature. There's something called gather, that's for that purpose. And that the gather will suppress your vacuum or keep your vacuum stable. So then, once the gather activation is done, then I move my package upside down, and using a solder preform, I glue or I solder the lid to a package. So this is not very simple. So you have to have temperature control, vacuum control, and you know when this heats up in the vacuum, you need to cool it, and then that's why we have like water coming in and then coming out so that we can cool it in vacuum. So results, if I jump into the results, before and after. So when I package this, so quality factor is a measure of how much loss you have on your device. So if it's a small number, you have a lot of losses. My quality factor of 20 went to 23,000, and I ended up with this nice curve. In other words, the vacuum packaging was successful. So together, so this is common in the MEMS industry, the MEMS people know this. So when you don't have any active pump when you seal your lid to the package, then your vacuum is not stable. Or you can't reach to the levels that you want. So this together is, people use titanium. So whenever something outgasses in the cavity, this titanium reacts with that gas and keeps your vacuum low. So the weird shaped fingers. So this weird shape, so these are called shaped fingers. Normally, if you have a straight finger, your capacitance is epsilon A over D. It's still the same, your capacitance is epsilon A over D, but you have to add them point by point. So the gap function here is it follows a 1 over x curve. And then when you calculate the force here, what you end up is, so you have a bunch of constants. So these are all constants, times x, x is your displacement. You can think this as F equals k times x, but that k is voltage control. And you have a mechanical spring as well, which is k times x. And this thing combined with your mechanical spring can reduce your effective spring constant. And this is called frequency tuning. So you can tune your frequency. Since the frequencies are important for a gyro, so you can use this to tune the frequency. What is the advantage here? The advantage is normally you use parallel plates, which are extremely nonlinear. With this has no nonlinearity problem, or like very, very low nonlinearity compared to parallel plates, and you can have very high displacements with no issue. And you can place these both on drive and sense modes. So more complicated one is the softening nonlinearity. So as I said to you, because of this, and that was dominant in my device, because of the nonlinear capacitances on your device, parallel plates namely, when you go to high displacement, so this is a simulation, and so these dash curves and solid curves are when you sweep the frequency one way versus the other, you see a different response. And because of softening, it bends towards left, and as you increase your displacement, your frequency reduces. What we are doing here is the same idea. So this is a cubic nonlinearity, and if I shape my gap as a function of x cubed, then what I end up is I can generate a cubic force, and this is DC controlled, and this force can be used to cancel the nonlinear force from the device. These are the measurement results. So here, so this red curve is when I don't have any tuning. My curve is bending left, and I gradually increase my tuning voltage. As you see, at 11 volts it becomes very linear, and at 14 it becomes the other way because I am introducing a hardening to a softening nonlinearity. So this is again a similar plot, but this time I went from 5 microns to 8 microns. When I go towards left, at one point my nonlinearity is suppressed, but I have different problems here. And that problems is, I think there are other nonlinearities coming in, the higher order harmonics, and that's why causing this. And if you increase your 15 microns to 20 microns, then this problem disappears. This 15 microns is the distance in between this tip and the anchor. As you make it larger, it becomes better. So this is the error variance result. So the long-term drift is there. So by long-term drift, I mean this right-hand side. Here, what I'm doing is I'm increasing the displacement. My signal-to-noise ratio should improve. In other words, this curve should move down. But what happens is at this 10.7, so my curve moves down, but my drift increases. But when I kick in my nonlinearity tuning, then I get better results. So this means my approach is working. So there is one problem here, which resolved later. So it had more noise than what it's supposed to have, but that was due to a PCB. So my stress study, so this is one of my first stress study results. So I have a chip and I have a heater. So So when I apply heat, then that will induce some stress on the device because this thing is fixed from the bottom. What happens is when you apply stress, it will open up like a flower. And when I do sweep the heater power, when I make it hotter and hotter, so for mode 1 is vibrating in one direction, mode 2 is vibrating in the other direction. So I see a discrepancy between mode 1 and mode 2. So this turned out to be the stress effects that I mentioned to you. Since this ceramic package, the one that I use is a long rectangle, it ends up being a different stress on X versus Y. And that pre-stress conditions the device in a certain way, and which results in this direction, in this response. But when you rotate the device 45 degrees instead of mounting it straight, if you rotate it, then you get a match in between whatever you're doing. So going into the real stress compensation results, so these are the stress sensors that were designed. So the stress sensors, see, silicon is piezoresistive. In other words, its resistance will change when we apply stress. So if you make a resistor like this, it's fixed from two ends, then whenever these two anchors displace, then you'll have stress. But the problem is, this is also sensitive to temperature, because temperature coefficient of silicon has temperature coefficient of resistance. In order to suppress it, there is another resistance. It has the same resistance, but it's just fixed from two ends, that there are no anchors. So this thing is not sensitive to stress, but sensitive to temperature. And if you connect these in a Wheatstone bridge, so if you connect these, then you can measure the stress by cancelling temperature. So these are the tests. If you increase temperature, both of them. So I call this R stress, this one R no stress. They follow the same curve. But when you stress them, so this is a temperature test, when you stress them, only R stress responds and R no stress does not respond. So this is the stress sensor. So this is one of the first results. So I have a gyro running. I'm measuring x-axis stress, y-axis stress, and temperature at the same time. And this is the blue is my gyro output. So if you look at temperature starts from 0 and it kind of comes back to 0. But if you look at the gyro, it doesn't come back to 0. It passes 0 and goes somewhere else. And if I look at my stress sensors, they look like the gyro output. So this was the first hope that the stress sensing is helping. And in order to make things better, so let's get rid of the temperature. So we have a temperature set up here. So this is how it looks like. So this is my PCB. So I have an aluminum block. A heater comes into this aluminum block. And I have 4 stress sensors in the device. And I'm using one of them, one of the resistors for temperature sensing. The temperature controller looks at that for temperature control. And I fix the temperature here. And I also have a copper weight. So what this weight does is I move this weight from left to right, right to left, and change stress while keeping the temperature constant. So we wanted to get temperature out of the picture so that we can see pure stress effects. And this is the result. So this is the gyro output. So the red one is when you, the uncompensated output. The copper weight left, right, right, left. And if I look at the stress here, one of them, so I'm measuring 3 stresses, one temperature, x, y, 2 x's versus 1 y. So temperature is plotted here. So the temperature, I mean, it has some shape to it, but it's not as square as this one. But if you look at the stress here, the S3, the blue one, so this is very similar to this. Then I find the coefficients in between this and that, and I compensate, and I get this 0 result, or compensated result. One problem here is some of the stress sensors, so S's are stress sensors. For example, S2 doesn't respond to anything. So S1 doesn't respond much, but S3 responds. So this is, I think, due to the mounting of our device. I think we had some problems with that mounting technique, which I will show. And if we plot the Ln deviation, so uncompensated is the solid one. And when we try to temperature compensate, which is this diamond curve, doesn't do anything because temperature is not changing. But when I do stress compensation, then I can get an improvement on the Ln variance. So this is a proof that stress compensation is working. One more, let's make things more accurate. Let's remove the weight. There is no weight. And the device is sitting on the table. Temperature is constant. And I'm collecting the gyroscope output. So the uncompensated one is the red one. Gyro is sitting on the table. I'm not rotating it. I fixed temperature, but it's still drifting. And the temperature is here. So in general, we plot temperature versus frequency because frequency is a strong function of temperature in general because of material properties. And temperature is not changing. It's very stable, like it's 40 millikelvin stable. And frequency is very stable to 10 millihertz. So this is drive axis stress. This is sense axis stress. But if I look at S3 again, so there's a strong correlation in between these two. And then if you run your compensation, you get this blue curve, which is more stable. And if I plot it on your invariance, it looks nicer. So the biggest problem in the MEMS server is this side, because it drifts more and more. But when I apply my calibration, then it goes down like a white noise. So this is like you reach to 10,000 seconds, which is 3 hours, and the gyro is still doing good. And the long-term drift is suppressed, which was the goal of the study. It is kind of, it is obtained. But how stable are these coefficients? So I run this test one day, run it again in the second day, and then compare my coefficients. And this is, I ran these test 1, 2, 3 different days, and these are all 12-hour-long tests. And you see the variance curves. So you see optimized coefficient and average coefficients. Optimized coefficient is like compute the coefficient for each test. And the average coefficients is I have 3 coefficients from 3 tests. I average them and I apply it to the first one. It is, I mean, there's a repeatability problem, but to the first order it is working. And here, this is the calibration of the gyro output in 3 days. So if you don't compensate it, it shifts this way. But if you compensate it, it is still not perfect, but a lot better than what it used to be. So discussion on die banding, why my stresses are not uniform. So this is how I mount it using that monofoil thing. I apply a voltage and it's mounted at room temperature. So later I heat it up and I look at it again. And this is the backside, as you can see, there are lots of non-uniformities. So this is something that needs to be studied. So one other thing we found was the stress versus no stress resistors. So it works as a stress sensor, but their thermal paths are different. So that's why one of them heats more than the other because of the thermal length. This is one found problem. And next is fixing it. How do we fix it? We anchor it from both sides. So this is our stress versus no stress. Our stress have more anchors. That's why it cools more. This thing heats up more. So what we do is instead of doing this, if you just connect it from, if you make the thermal paths the same, then it will work. Or we can use, these ones require a voltage and they heat up actually. They act like heaters because this is a resistor. We can do capacitive stress sensors. So future, I'm almost done. The future research, so what do we do next? So this is what I want to do next in these days. So if you have a circular gyro, one anchor in the center and the stress sensors on the outside, then you can measure whatever the anchors are doing more accurately. Because if you do a rectangular gyro like I did, it has distributed anchors and you measure stress on the sides. So that may not be the best efficient. So my argument here is if I make it like this and have my stress sensors on the outside, and I can measure and I can have more repeatable results. And I can use a stress sensor like this, so this is called a stress rosette. You measure X, Y, and shear with this. But instead of using piezo resistance, you can also use capacitive gauges. These are nicer. These have been proposed like in 2002 by University of Michigan guys. And the advantage of this one is this doesn't have any heating problem. This is capacitive. But the readout is more complex compared to that one. So this type of a capacitive strain gauge can be designed. And die attaches, so they are a universe. So by using an array of this on a substrate, so you can change temperature, apply stress, and look at how different die attaches respond to stress. And the nonlinearity and stress can also be combined because nonlinearity is the cubic stiffness, for example, depends on stress as well. So that could be done as well. So this is one more thing, not a gyro. So what I thought was, if you have a cavity, it has an acoustic resonance. And that acoustic resonance depends on the speed of sound in that gas. and that determines the frequency. If you couple the acoustic resonance in a cavity with a MEMS device, then when the gas composition changes, then you can have a gas sensor. In order to solve the temperature problem, so you can have two of them running, one of them sealed, one of them not sealed, so that temperature cancels. And if you do such a configuration, the other problem is selectivity. You can't distinguish between gases. And in order to do that, if you also monitor the damping is also a gas property. And by monitoring the damping and the frequency at the same time, then I believe you can make a gas sensor. This is what I'm going to try next. My final slide. What I haven't talked about is how you develop, because I work in analog devices, how you develop gyros in industry. So this is a released product. This is ADXRS290. So the first thing, so it should be plug and play. So when you have the gyro, and it can't be so big, so it requires an ASIC. So this thing has everything inside. It doesn't have a like big lock-in amplifier box like I will take this and it works. It's like 6 millimeters, like 5 millimeters. And you can't use extreme voltages. There's no 200 volts, for example. Size is a major concern. So when you want to put this in your cellular phones, the size gets even smaller. So you have to do this in a less than a millimeter square area, for example. It should be robust over manufacturing variations. So when you manufacture them again and again, it should give you a consistent result. And it shouldn't work at a certain temperature. It should work in a temperature range in a well-behaved way. It can't do weird stuff. And the other, more important, this is also important practical consideration, it should be robust against vibration. For example, if you put it on a car when you are driving, if the road is bumpy, there is a lot of vibration, your gyro cannot rail. Because if it rails, then it will trigger other safety mechanisms, and these things are very serious. So designing a gyro in the industry is different than academia. So you have to pay attention to practical constraints very significantly. And this is all. I'll be happy to answer if you have any questions.
Okay. So if you think that your PhD subject was difficult, I guess you appreciate now your PhD subject. I mean, this included electronics, mechanics,